The general power rule is a type of chain rule that helps us differentiate u to the n, where u is a function of x. The derivative of u to the n is n times u to the n minus 1, where we pop the n down and then power down, subtract 1 from the power. But then the chain part of it is that we have to also multiply it by u prime, the derivative of this inside x function. Number 1, to differentiate, I'm going to establish what is u. U is x squared minus 3. What would that make u prime? 2x. Differentiate, pop this power down, multiply by u, subtract from the power, and then multiply by u prime. We usually like our answers to be fully factored, so we'll multiply the 2 and the 2x, but keep it in front of the quantity x squared minus 3. For number 2, I'm going to rewrite this radical as a power. Now I'm going to differentiate using the general power rule. I have a function of x, not just x inside here, so u would be the function of x, 2x squared minus x, and u prime is 4x minus 1. Pop down, power down. What goes inside? U. What do we multiply by? U prime. This is already factored. Either one of these answers is acceptable. For number 3, we have several things going on here. I see that I can rewrite this radical as 9 minus 4x squared to the 1/3. That's going to require general power rule. But what about this 3x squared in front? If it were just a 3, I could use the scalar multiple rule. But there's an x in here, which requires me to use the product rule. We'll begin with the product rule. Identify f and g. F times the derivative of g plus g times the derivative of f. We established earlier that this would require us to use the chain rule because we have a quantity of x to a power. So u will be 9 minus 4x squared. That makes u prime negative 8x. Pop down, power down. U goes inside. U prime is multiplied here. The derivative of 3x squared is 6x. This is not fully factored because I have the sum of two products. Let's simplify the first product as much as possible and then see if we can factor. Again, we're not fully factored. Is there a common quantity between the two products? Yes, 9 minus 4x squared. We're going to factor out 9 minus 4x squared. You may be slightly confused because these are fractions and one of them is negative, but factoring, we just take the least amount that's in common. So literally the least amount. What's smaller, negative 2/3 or 1/3? Negative 2/3 is smaller. That is the exponent of 9 minus 4x squared that we're going to factor out. Remember, factoring means dividing. So we're basically dividing each of these products by 9 minus 4x squared to the negative 2/3. When we do that, here we get a special form of the number 1. So the first product divided by our GCF is negative 8x cubed times 1. Plus, our second product, when we divide it by our GCF, is 6x times, because each of our exponents has the same base, our property of exponents is that you can just subtract those. So it would be 9 minus 4x squared to the 1/3 minus negative 2/3. That's 1/3 plus 2/3. That's 3/3, which is just to the power of 1. Let's distribute and combine like terms in these brackets. This piece still has a common factor, so I'm going to take out a negative 2x. Now I'm ready to write my answer as a fraction. My denominator is 9 minus 4x squared to the 2/3, or you can write it in radical form, and the numerator is negative 2x times 16x squared minus 27. And that is our fully factored answer for differentiating a chain rule within a product rule. So when do we use the chain rule? When there's a composition of functions. Deriving x squared requires the power rule. But deriving x minus 1 squared requires the chain rule, where you take the derivative of the outside and multiply it by the inside, and then multiply it by the derivative of the inside function. So the way I say that is the derivative of the outside times the inside times the derivative of the inside. And that is our chain rule. Sometimes they're not even going to give us functions, and we'll need to determine based on the rules that we know. So what they're asking here is the derivative of p of q of x at a value 2, and they've given us select values of p and q and p prime and q prime. The derivative of p of q of x is p prime times q of x times q prime of x. If we're evaluating this at 2, let's replace the x's with 2's. This is p prime of q of 2, so I can't evaluate p prime until I figure out what q of 2 is. Q of 2 is 3. Q prime of 2 is 2. What is p prime of 3? That's 4. 4 times 2. Our derivative of p of q of 2 is 8. If f and g are the functions whose graphs are shown, let u of x be f of g of x, v of x is g of f of x, and wx is g composed with g of x. Find u prime of 1, v prime of 1, and w prime of 1. U of x is f of g of x. So u prime of x, the derivative, will be f prime of g of x times g prime of x. If we're evaluating that at 1, g of 1 is the y value for g at x equals 1. That is 3. G prime of 1 is the slope of the g graph at x equals 1. You can see there's a line here, and the slope of that line is negative 3 over 1. F prime of 3 is the slope of the f graph at x equals 3. The f graph has a slope of negative 1 over 4 at x equals 3. U prime of 1 is 3 over 4. Try doing the next two on your own and then check when you're ready. F of 1 is 2. F prime of 1, the slope here is up 2 over 1. We already figured out g of 1 and g prime of 1. So the last value we need to find is g prime of 2. The derivative of g at 2 is, there's a sharp turn here. Sharp turns are not differentiable, meaning you cannot find the derivative at a sharp turn. So g prime of 2 is undefined. Now simplify. This makes v prime of 1 undefined. And that's how we use the function values and the derivative values of graphs to use the chain rule.